Hi, my name is Zheng Yao from Danjiang University. My research interest is the R number theory and representation theory. More specifically, I'm interested in algebraic number theory and automorphic representations. And I guess the keywords of my research are L functions and Lagrange programs. So now, instead of describing my work in this short amount of time, I would like to introduce this keyword and hope that you will have some feeling about what I'm concerned about. So now, an L function, according to Wiki, is a meromorphic functions on whole complex plane that attach to certain mathematical object that usually satisfy some properties. And in reality, the L function usually defined by the infinite products, which are also called the Euler product. So a priori, the L functions are only defined for real part is larger than not. And in many cases, we don't even know that it can be meromorphic continuum to whole complex plane, although we still call them L functions. Now, I guess the famous example is Riemann zeta functions. And as you can see, the functional equations are relating S to the 1 minus S. And in a slightly general situation, we have the Dirichlet functions, which recover the Riemann zeta functions when m equal to 1. We also have the L functions attached to Gauss representations. And as you can see, it's defined by the Euler products. To list more, we have the L functions attached to modular forms or automorphic forms. And we also have the L functions attached to elliptic curve and the Hasse-Weil beta functions attached to algebraic varieties. So now I guess the natural question is, what do we care about? Given a L function, of course, we would like to know if it can be meromorphic continuum to a whole complex plane. And in addition, we also want to know some analytic properties of L functions, such as we want to know that the location of pole and zeros. And we also want to know that some algebraic property of the L functions. For example, we know that the Riemann zeta functions at the even positive integer is equal to some power of 2 pi I times the rational numbers. And we would like to know that if this phenomena continue to hold for general L functions. So now, why we care about that questions? One of the reasons is that there are many conjectures relating to these questions. For example, we have the Riemann hypothesis for zeta functions, and we have the BSD conjectures for elliptic curve. And but more importantly, understanding the L functions help us understand the object that is attached. Now, in modern number series, we usually study L functions by using certain harmonic analysis. And I guess this approach first appeared in John Tate's PhD thesis. Okay, and here is where the representation theory comes in. Now, in the final part of this talk, I would like to briefly describe our guidelines. Now, given an L functions, why we expect that it will have meromorphic continuation, and also how we prove that. And our guideline is Lagrange programs, which predict a lot of phenomena in mathematics. So because of that, some mathematicians also regard it as a kind of grand unified series of mathematics. Just to give you a feeling how powerful Lagrange program is, I just mentioned that in Weyl's proof of Fermat's last theorem, one of the major steps is to show that every semi-simple elliptic curve over Q is a module. But this is really a special case that predicted by Lagrange programs. So this concludes my talk. Thank you for your attention.